I'm Luke Van Hooser, and this is my Physics Lab 5. The purpose of this lab is to measure the effect of Faraday's law on the falling speed of a bar magnet and compare it to a computational model. Physical principles involved in this lab are Faraday's law, induced current, and the Biot-Savart law. Procedure. A bar magnet was dropped through a vertical roll of aluminum foil. The bar was filmed so that the time it takes the bar could be recorded. This is later going to be compared with a coded simulation. So I ran 5 trials and took the average. For trial 1, I got a time of 2 seconds. For trial 2, I got a time of 1.875. Same with 3 and 4. And for trial 5, I got a time of 1.75 seconds for an average of 1.875 seconds. The additional data were the length of my foil, which I found to be 30.5 centimeters, the width of the foil, which I found to be 1 centimeter, and the inner radius, which I found to be 2.8 centimeters. So for my code, I started by entering the values of my aluminum foil tube, and then defining a function that calculates the magnetic field of a magnetic dipole. Next, I created a function to calculate the differential of flux over time for individual rings throughout the cylinder, and then add up each ring across the cylinder. So for the velocity versus time graph, this is what my code showed, which shows a decrease in velocity, a linear decrease in velocity throughout the 0.225 seconds that the model calculated the magnet spent in the tube. Additional questions: what if the resistivity of the conductor were reduced to as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity was close to 0, the induced current would be greater, causing the magnet to fall more slowly. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes would increase resistance, which would cause the magnet to fall faster. Additional questions. What would happen if you flip the magnet around? The magnet's fall would be unaffected. How does the time of the computational model compare to that of the experiment? How might the computational model be made more accurate? The computational model showed the magnet falling much faster than it did in real life. This could be because the model ignores other factors affecting the fall, like friction of the magnet hitting the inside of the tube and air resistance. What does the shape of the velocity versus time graph say about the forces acting on the bar magnet? Gravity causes an initial spike in the velocity, which is gradually reduced by the induced current of the tube. That's my Lab 5 report. Thank you very much.